Good. So hello, everyone. Welcome back to the Advanced Machine Learning lecture series. I will start as usual with a small recap of what we did last time. We started talking about active learning. And so what we mean by active learning may be a scenario like the one shown here, where you have many training samples, but most of those are not yet labeled, and labeling is expensive. So for example, labeling may be done by a human, or labeling may mean that you have to run another expensive experiment. And so you want to concentrate on those training samples that are most meaningful for you to gain a lot of extra information. And so that is one goal of active learning. And last time we discussed that typical method to achieve this goal is just to go for largest uncertainty. So you ask your model, you ask your neural network what it thinks about any of the unlabeled training samples, and you choose the training example where it is most uncertain in order to label that next and use it for training. That works very well when the task is classification, because typically the output of the neural network is like a probability distribution, so it can be used naturally to indicate uncertainty. It's much harder if you have a regression task, so you want to fit a function, you want to have the output being some number, then you don't necessarily have a natural indication of uncertainty. But you can circumvent this, for example, if you have a committee of models. This is something we discussed last time. You train multiple models, and then if they agree very well, the uncertainty is small, obviously, otherwise uncertainty is large. There are also other techniques which we will learn at the end of today's lecture. Now that's active learning, more in the spirit of, I want to train a neural network, let me pick the best training samples. And connected to that is a slightly different direction where you say my model is not really a neural network, which has many, many parameters, but rather it's a model that I have constructed based, say, on physics principles or some other kind of model that describes the real world. It may have much fewer parameters than a typical neural network, but still I want to figure out these parameters, and I can do so by running an experiment. This experiment can be run in many different ways, so there are some measurement settings that I can choose. And I want to choose them in a way that I gain the maximum amount of information really quickly, so that I will quickly learn the unknown parameters of my model. And this is what we want to discuss today. Okay, so we started already a little bit with that direction. Last time we said when we talk about a model now, we will assume that somehow I have access to a probability distribution that describes the outcomes of measurements. So these outcomes of measurements do depend on unknown model parameters, here called lambda. But of course, the outcome of the experiment also depends on the choice of your measurement settings. So that may be some voltage that you can set, or some mechanical parameter like the velocity of a particle. You can choose that for your measurement. And of course, the measurement result will depend on both the unknown model parameters and also these measurement settings that here we call x. And so this conditional probability to get a certain measurement result, given the setting and given the model parameters, this is the input that we will need that describes our model. And once we have this conditional thinking, it's pretty clear that the best way to update our information about these unknown model parameters is by using Bayes. And so this is what we will actually do. We also gave a little example from physics. If we had some oscillator with an unknown frequency and unknown damping constant, then the unknown model parameters are clear, frequency and damping. The experiment I might conduct would, for example, consist in setting some initial values for the location of the particle and the velocity. So that would be x. These would be the measurement settings, so to speak. And then finally, I run the experiment and I read off the coordinate of my particle at the final time, but there's some measurement noise on top of it, and that would be my measurement result y. And then taking everything together, this deterministic trajectory plus the noise in the end, I could indeed write down a probability distribution of the result y conditioned on where I measure, so x, and conditioned on my unknown model parameters lambda. Okay, so we said, let's use Bayes. Let's use Bayes to update our information. So we already know how this works. And in this little section today, we will be able to use many of the techniques that we learned when we discussed information theory. So I would say the probability distribution of lambda given the observed measurement result, according to Bayes, is of course when I switch around the order. So the measurement result given lambda times some prior probability over lambda. So that would be P0 of lambda. And then finally, we still have to divide by a normalization. So if I integrate the right-hand side over lambda, I should get 1. And so if you think about it, you need a normalization factor that turns out to be simply the overall probability to achieve a measurement result y independent of what exactly is the value of lambda. So this would have been whatever is in the numerator integrated over lambda. And so here I'm imagining for a moment these are probability densities. If I have discrete events as usual, I would have sums. And so what we have on the left-hand side, of course, we already know this is called the posterior distribution over lambda. And that represents how we update our knowledge of the world. So we could imagine a situation where lambda initially, we don't know much about it. So that would be my prior. And after we take a measurement result, even though there's some noise involved, we can update lambda and get another distribution, which hopefully is much more concentrated. And that is the posterior. Okay. And then you will continue to make measurements like this. And in a moment, we have to ask what are the best choices for X in order to gain as much information as possible. But in any case, you will continue to make measurements like that, which will shrink your distribution. There's one important thing in this whole game to understand. So whatever we have written down right now is from the point of view of the experimentalist who does not know the correct value of lambda, who has only some vague prior distribution, and then tries to update using Bayes given the observed measurement results. But of course, the real physical system that has one particular fixed true value of lambda, and if you make a sequence of measurements on the same system, they all relate to the same true value of lambda. So that's very important to understand. Even though we don't know this true value, it is in the background. And sometimes I might call this lambda star. And this true value is important because whenever you do a measurement, the true probability distribution for the y values for the measurement results depends on this lambda star, not on anything else, just on this lambda star. So y is distributed according to the distribution that is conditioned on lambda star. And it remains so even when you do the next measurements in your sequence, because you always keep the same underlying physical system. In any case, once you have calculated your posterior after this first measurement, you can go to the next measurement, and the posterior that we had now becomes the prior for the next update. So we can just continue on the scheme, and the typical way this looks like is you have a very broad prior. I now plot it like this. And then after one update, you get already something sharper. And then you have another update and it's even sharper, and another update, and hopefully it's even sharper, and so on. Okay, so that's the measurement sequence. And you would hope that the distribution eventually concentrates near lambda star. And when we discussed Bayes, we also had a quick discussion of some mathematical results that indicate, yes, Bayes is consistent. So if you do sufficiently many measurements and nothing really bad happens, then you will concentrate near lambda star. But the question is, how can we speed up this process? And the one choice we have that we can make in every of these measurements is the choice of X, the measurement settings. We can choose that. And so it would be smart if, given all the prior information, the current distribution over lambda, for example, and our knowledge of the model, can we be smart in choosing X so that we gain as much information as possible? Now, that brings us, of course, to a quantity that we have discussed previously, which is the information gain. So I just recall for you how we define the information gain. In such a Bayes setting, we would say the information gain, given that I have measured the particular value y, we can define as the difference between the original prior distribution and the posterior distribution. And we can measure this difference between the two in our usual way using Kullback-Leibler. Okay. Now, this is to classify what's going on and how much your probability distribution becomes sharper for a particular value of y. But before we do the measurement, and when we still have to decide which value of x to pick, of course, we do not know which value of y we will eventually get. So what we are really interested in is to calculate for any possible choice of x the expected information gain. Expected here means to average over all possible outcomes y. And of course, we have to average over y according to the distribution that we expect from our current lambda distribution and from our model. And now it turns out, and I think we discussed this before, that this expected information gains, so the average over this Kullback-Leibler, is exactly the same as the expected reduction of the entropy. So again, that would mean you calculate the entropy over the prior. That's a measure of how widespread is your lambda distribution. And then you subtract the entropy, the conditional entropy. And now when we write it like this, you remember, this is not the entropy for a particular value of y, but it's the entropy where I already average over all possible values of y. And so I can write this down more explicitly for you. The first term would just be the P0 log P0 of lambda, the entropy of the prior. And the second term would look like this. I would have the entropy for the conditional distribution, so the posterior, given that I have measured a certain value. And then I still average over all possible values. Okay. And then you can work this out. And another way to express these things is to say, oh, this is the mutual information, actually, the mutual information between two random variables, one of which is my model parameters, and the other is the outcome of the measurement. And so, not surprisingly, you want to choose your x such that the mutual information between the model parameters that we want to figure out and the measurement outcome y is maximized, because then they have to do they have something to do with each other. And by looking at the model, by looking at the measurement, you can learn something about the model parameters. Okay, so this is what you want to do. You want to, before you do any measurement, you want to calculate from your model and your current lambda distribution the expected information gain as a function of x, and then you want to pick the largest information gain. So here, if we want to make a little plot, this is the expected information gain as a function of x, and let's say it looks like this. And then, of course, in that case, you want to do your measurement precisely at the point where you expect the information gain to be largest. So that would be your x star, so to speak. That's the preferred value of your measurement settings. That's where you learn the most. Okay. And so the question is how to implement this in practice. And one way to do this is really to look at all these probability distributions on a grid. This is still possible if all the variables that we have here are sufficiently low dimensional. So which variables do we have? Well, this is obviously lambda, the unknown model parameter. We have x, the measurement setting, and we have y, the measurement outcome. So if lambda, x, and y are all low dimensional, I can calculate all these probabilities that we're playing around with, like the prior distribution and in particular the model distribution and so on. I can calculate all of them on a grid. So I would have, so to speak, 3 axes. If they are all scalar quantities, I would put a grid here. And even then, I already have, if I want to store something like the model distribution, so the probability of a certain measurement outcome given x and lambda, this will already be a 3-dimensional array. So it has 3 indices, 1 index for lambda, 1 index for x, and 1 index for y. And you can imagine how the effort grows if you go to higher dimensions. Now, I want to show you one example on this level to illustrate things, unless there's a question already here. So the setting is clear. We have a model. We can calculate the expected information gain, and we are smart. We choose the measurement with the largest expected information gain. Okay, so let me jump to the model. The model situation I want to consider is, again, physics inspired. I imagine that there is some interesting object, some kind of scatterer, some particle, that is at an unknown location, which I don't know. This location would be my unknown model parameter lambda. Let's say the vertical distance, that is lambda. So I don't know the location, but what I can do is I can have a particle, a test particle, be injected into the setup, and it starts here, and it will be deflected by this unknown particle that I want to figure out where it is located. So this is the test particle, and I can send it off in a direction that I will call phi, that's the angle. But of course, in our language, that would be x, that would be the measurement setting. And so it flies by the other particle, it gets a little bit deflected, and eventually I will measure where exactly it lands. And so in this case, in my model, the vertical distance that it has traveled at the end, that I will call y. That's my measurement result. And so now the question is still, where does statistics come in? I could have said that I cannot resolve very well the final location. That's one possibility, some measurement error on the location, the final location. But I decided to make things more interesting, and I just imagine that there's a fluctuating force acting on my test particle. So the real trajectory is a little bit fluctuating, and maybe then it ends up at a different spot. And every time I run the experiment, it will end up at a different spot. So we'll eventually get a probability distribution, and that defines my model of the conditional probability for a given measurement result given x and lambda. Okay, so how does this look like if I show these trajectories to you? So what I've done here is I imagine that I have my unknown particle sitting at some spot, I believe it is here. And I run many trajectories with different initial angles, so different measurement settings x. There's always a whole bunch of trajectories starting out with the same x, but they end up at different spots simply because of these fluctuating forces. And so if you pick out one of those bunches, like this one here, you can also look at the final locations of each of these trajectories, and you could make a histogram. And this histogram really would represent the probability of a certain outcome of my measurement given, in this case, the particular value of lambda that I assumed. Okay, so on the horizontal axis, you would have y. And it's normalized such that if you sum the bins, you get 1. Now, what you can do is, this model has been defined just by the equations of motion, including the fluctuating force. And you can do Monte Carlo, so to speak. You can run this model simulation many, many times for different assumed values of lambda and different values of x, that is the angle of the trajectory at the starting point. And you can record the final value of y. And this gives you, so to speak, the model distribution. And I try to plot this here. So that would be the conditional probability, getting a certain outcome y, given x and lambda, where x, that is my angle that I can choose, is plotted on the horizontal axis, and y, the measurement outcome, is plotted on the vertical. And I've shown these plots for different values of lambda, because we don't know which lambda we have eventually, so I have to really run my model for all possibilities, for all possible lambda. And you see, as lambda changes, also the features of this plot change. So you see that there is a particular feature that keeps shifting around depending on how you choose your lambda. Problem being, of course, that initially we do not know the correct value of lambda. And the goal will be, as we learn more and more information, to pick x such that if I run the measurement at this particular x, it will be most helpful in distinguishing the different possible lambda values. Okay, so we know in principle how to do this. We have to calculate the expected information gain. And you can do this once you have the model distribution available and you have the prior available. So this is what I did. Now let's discuss this plot. What you see in the first row is always the distribution of lambda, and the different columns as we go from left to right represent a measurement sequence. So I start on the left and I measure multiple times. Now what I see here in the first panel on the upper left is this is the prior distribution. Yeah. So I assumed it to be roughly a Gaussian that is cut off at some values. Lambda is plotted to the right. Now that's the prior distribution. I also indicate for you the true value of lambda that is assumed in this measurement sequence. So that would be the true value of lambda. But the funny thing is, of course, when we are running this experiment, we do not know the true value. It's hidden for us. Only later, maybe someone can tell us, oh, that would have been the true value. And then we can compare against our thinking, for example, against our lambda distributions that we had updated. Okay, so this is the prior distribution. And now from this prior distribution and with our model of the measurement process that I have obtained by running many simulations, I can do this calculation of the expected information gain. So this is here shown in the second plot just below. This is the expected information gain. So the expected average reduction of the entropy plotted for different possible choices of X. But there is a question. So whether I have assumed that the target particle is way heavier than the test particle. Yeah, that's a very interesting idea. Yes, indeed, in this physical scenario, I have assumed that the target particle is way heavier than the test particle. And so that means when I run an experiment, it can't change its position. And I like this question very much, because you know that in quantum mechanics, of course, it is unavoidable that a measurement can do something bad to a system. But in principle, even in classical physics, this can happen because if, for example, the test particle and the target particle have a relatively similar mass, then of course, any test particle could push away my target particle, at least by a little bit. And so this would have to be incorporated actually, and that would make the whole thinking more involved. I like this question because the the test particle, we said, is subject to these fluctuations. So even if I started deterministically in a certain direction, I cannot know for certain which trajectory it will take, and I'm only measuring the final location. So I don't know what happens in between. So it will give a random fluctuating kick to the target, to the target particle that I want to determine. And so this would actually make things quite a bit more interesting. Yeah? Maybe that would be a good exercise. Yeah. Anyway, so there's an interesting connection between quantum physics, where such effects are fundamental and completely unavoidable, and classical physics, where, at least in principle, you can always imagine the test particle is very lightweight and so on. But you can also model some such effects. Okay, so now leaving aside this complication, just imagine we did some measurement at a particular location X, and we can record what is the corresponding expected entropy reduction, and we get a certain value. Then we repeat the same thought experiment at another X and record the entropy reduction, we get another value. And if we plot this against X, we get the interesting curve of the expected information gain, and we can simply pick its maximum. So in a more general setting, you might want to do gradient ascent to find the maximum. Here I had everything on a grid, so I just picked the largest value. And in this first measurement, the best choice for the angle phi, that is X, is still 0. This is simply a consequence of symmetry. So the lambda distribution was symmetric and the model was symmetric and everything was symmetric. So you expect that initially for the first measurement, if you don't know anything else, you should shoot the test particle horizontally at phi equals 0. And then the last panel here shows the distribution of measurement outcomes for this particular choice of X. And you will notice, if you look closely, this distribution is shifted. It's no longer symmetric. And the reason it's no longer symmetric is because it has been calculated for the actual true value lambda star. And this lambda star is not sitting at 0, it's sitting somewhere else. So that gives a certain asymmetry. And in particular, the lambda star I assumed here is such that the target particle actually does not sit in the upper half of the screen, but in the lower half. And so for any test trajectory starting off at 0 angle, it will actually be typically deflected upwards. So that's the physics. Yeah. Okay, so then I have to draw from this distribution to simulate the actual experiment that happens. I get one value of y, nothing more. So a single value of y. I don't get any distribution or so, just get a random sample of y. And then this is the only piece of information I really get from the experiment. Now, once I have this information, I produce this posterior for the first measurement from the Bayes update, just as usual. So that's the first measurement. You see it's tilted. It goes in the right direction. Everything has been shifted to the left. So because the particle has been deflected upwards, it knows, aha, the true location of the target particle is probably sitting down. So everything has been shifted. Then I can go through the same motions again. I can calculate the expected information gain. And now suddenly it has a maximum at some angle that is a little bit shifted to the left, because if the target particle is sitting in the lower half of my space, then it would be good to shoot directly towards it. And then if I actually do this, I get a new distribution of measurement outcomes that's shown here. I sample from it, and then I go on and on. And as you can see, every time I do this, typically my lambda distribution shrinks. So the variance shrinks and also the entropy goes down. You may remember from our discussion of Bayes that it's not completely guaranteed that the entropy always decreases. Even though you have a new measurement result, sometimes it could happen that the entropy increases. It is only on average, if you average over all possible measurement outcomes, that the entropy has to decrease so that the information gain is actually positive. Okay. And so what you also see is that the lambda distribution has a tendency to concentrate more on the real value of lambda. But you also see that after this number of measurements, the maximum of the lambda distribution that we got is not, of course, the same as the true value. So that will happen only later when it converges even more. Okay, so that was one example. In this example, everything was low dimensional. Lambda was a scalar, x was a scalar, and y was a scalar. And I could do everything grid-based. I could run many simulations, Monte Carlo style, and collect the statistics. If I want to go beyond that, things become more difficult. And so maybe at least we can write down a little bit what happens if we go beyond that. So if everything else still remains low dimensional, only y itself, the outcome is high dimensional, then I might still be able to get away with sampling y. That could still work. If lambda is high dimensional, or maybe also x, then things are more difficult. And so one option we have these days is, of course, something we learned, namely to have a neural network come into play. So instead of storing the model distribution or the posterior distribution as an array, so to speak, that I have sampled with many grid points, I could just use a normalizing flow or some other method that allows me to represent probability distributions. So for example, I could use this to represent the posterior. So people have started doing this. These developments are already still quite new, only in the last few years, seriously using deep neural networks for Bayes updates and optimal experimental design. There's still a considerable amount of sampling involved. So sampling lambda, sampling y. And so it's still not so easy, actually. So once you have obtained your Bayes update, of course, you want to optimize X. Now, in the grid-based approach, you can just look up in your array what is the largest expected information gain. So it's direct. But again, that only works for low-dimensional examples. For high-dimensional examples, you can try to do gradient ascent in the information gain, provided you have a differentiable version of that. which can work if you have a neural network representation. It will not work if you have a grid-based representation. Or in principle, you could also use those gradient-free optimization methods that exist that only need to evaluate a function. So these are the possibilities, but I warn you, it's quite an effort numerically. Okay. So any questions here so far? Well, if not, then I want to switch to another section, the last section in this chapter on active learning and optimal experimental design. And this combines a little bit the different pieces that we've been talking about. In the beginning, we talked about neural networks and we said, okay, which training sample should I pick and how do I optimize this? And then we talked about models that are more physical models with a smallish number of parameters, and how should we then pick the best measurement that we can do to maximize the information gain. And we will now put this together and apply the thinking that we just outlined to generic models that are not coming from physics, but are just completely general. And we will discuss two things: Gaussian random processes and neural networks eventually. And so these are high-dimensional models, obviously. And so the interesting question is, how do things go there? They are high-dimensional, at least in the sense that a neural network would have many parameters, or also that a Gaussian random process would be described by many parameters. So the lambda is, so to speak, large, high-dimensional. So let us start with Gaussian random processes. And I think I need to remind you maybe a little bit. We discussed them some time ago in this lecture series. So what we think of when we say Gaussian random process is we think of, say, a function of time, let's say, or a function of a space coordinate, it doesn't matter. And it is fluctuating. So one realization might look like this, another realization might look like this, and so on. So fluctuating functions. And in our language, we could say that each of these processes corresponds to a different lambda, but only if we consider lambda to be a high-dimensional vector. And so in order to make our life easier, we do what we did when we discussed this. We might imagine that we discretize time. And that means instead of having a continuous function phi, which is even harder to model, we say we have phi represented as a vector, namely the vector of values at the different positions. So there will be a phi1 and a phi2 and so on. So phi will now become a vector. And now we imagine that we have a prior distribution over phi, just as we imagined when we first discussed Gaussian random processes. And that after you do a measurement, so you figure out what is the value of phi at a particular time point t, after you do this measurement, you can do your usual Bayes update. And we already did this actually for Gaussian random processes. So we can apply Bayes, which we did before. And we would say something like, what is the probability to find a certain realization phi of my Gaussian random process, or a certain fluctuating curve, given all the previous measurement results? So we would have, for example, at time t1, we measured some y1, at time t2, we measured y2, and so on. And there was some final time, I don't know how I called this, m maybe, and we would measure ym. Okay, so we can apply Bayes, and we did this. One thing that's important here to understand is that the y itself can be the process at this time plus some noise, because we imagine we have some measurement noise. So even if I tell you the value of y, that doesn't mean the value of phi is exactly the same. There's some measurement noise. Okay. And so the nice thing is that we do have an explicit formula for these kinds of Gaussian random process probability distributions, because they are simply multidimensional Gaussian distributions. And so let's say I'm still before the measurement. I would say P of phi equals, and now I'm just copying from what we did earlier. It's a multidimensional, simply a general multidimensional Gaussian distribution. So how does this look like? Well, phi is a vector and it may have some non-zero average. So that's phi bar. Also, there will be a correlation matrix, like for any Gaussian multidimensional distribution, there will be a correlation matrix. And then again, there will be phi minus phi bar. And if I want to do it correctly, there's 1/2 in front. And that is almost it, except we have a normalization factor in front. The normalization factor is quite interesting. It in particular contains the determinant of this correlation matrix. So that's the correlation matrix, C. And I imagine if there were already some measurements that have taken place previously, maybe P of phi is already a posterior distribution. And then both the correlation matrix and the phi bar have already been updated according to the set of measurements that have taken place previously, in a way that we actually discussed when we first discussed Gaussian random processes. But it's not so important. This might also be your prior distribution, and someone gave to you C and phi bar. And n is the number of grid points here. Okay. And we also remember the meaning of C. So CLJ would be the average of phi L minus the mean phi L times phi J minus the mean phi J. So it's the correlation or covariance matrix. Okay. Now, okay, there's a question. We do have the restriction to assume the noise only Gaussian. Right, yes. So the measurement noise I introduced here should be Gaussian, at least for my method to work. Otherwise, the time I do my first measurement, immediately I would go out of the space of Gaussian distributions and everything would become more complicated. That's a good point. That's also the reason why this measurement result should be linearly related to the random process, because again, otherwise I would have a problem. Okay, good point. So now we want to apply this idea of information gain. So we have to look for the entropy reduction. So the first question that arises is, what is the entropy of a multidimensional Gaussian distribution? Now, fortunately, that's no secret. You can look it up almost anywhere. And so the entropy of this distribution, let me write it in this way, is, well, there's a prefactor that depends on the number of grid points. That's not terribly exciting. But then there is another term, and that's a log of the determinant of my correlation matrix. So if you have only a simple Gaussian, then the correlation matrix becomes simply the sigma squared, and the determinant just becomes sigma squared itself. So you would have the log of sigma squared. Here it's more complicated. Okay. Now that's before the measurement, so to speak. What happens after the measurement? Well, and that's something we discussed when we discussed Gaussian random processes. So intuitively, what happens is, of course, if I measure and I find that the value at a certain time is within some small interval that I depicted here, then, of course, all the processes that are still compatible with this observation must go through this small interval. So they must look like this or like this. So there will be many random processes still possible, but they all have to go through this interval that was decided by my measurement resolution, so to speak. Now, what this means is two things. First, the phi bar changes, so to speak, the average, the expectation of my random process changes. But we will not be interested in this because, as you can see from the entropy formula, the entropy only depends on the correlation matrix. So the only thing I'm interested now in order to estimate entropy and information gain is to look at the correlation matrix. And we learned before that the correlation matrix after measurement has to be updated. So I write down the inverse of the new correlation matrix. And it turned out there's a fairly simple formula. It's the inverse of the old correlation matrix plus something. And what we have to add depends on two things. First, it depends on the location where I do my measurement. So this spot, what is the time point at which I have measured? And also it depends on the measurement uncertainty, whether I can do very precise measurements. And so the result is rather simple. So it's 1 over sigma squared, which is the measurement uncertainty. So this Gaussian measurement noise that we added, times something that for brevity I will write in this way. So x indicates the measurement location, which in our discretized world is just one point on this grid. So I have many points on my grid, and there is one point, and that is x, my measurement choice. Where do I want to measure? But what do I mean by x? Well, that's notation borrowed from quantum mechanics. I can indicate this as a matrix to you. It would just be a matrix where there's only a single diagonal entry being 1, and that is exactly at the spot given by x, both in the column and in the row. Okay, and the rest is 0. Or I could say, in terms of Kronecker deltas, both. Okay, now I have to be careful. If I were to take matrix elements, that would be Kronecker deltas. So delta n comma x and delta m comma x. Okay, it's the same thing. So we learned that previously. So that's the way you update your correlation matrix. One interesting remark here is already, this is independent of the measurement result. The actual measurement result does not enter of how the correlation matrix is updated, and therefore it also does not enter on how the entropy changes. And that is very nice, because otherwise we would have had to average over the potential measurement results. Here, this is not necessary, because things do not depend on the measurement result. Okay, so we don't need to average. So that's one trouble less. And now let's just calculate the difference between the prior entropy, which is written on the top of the slide, and the entropy calculated from this new correlation matrix after the measurement. So we would find h of the prior minus h of what happens after the measurement equals, well, there were these constant terms that are not of interest, but then there are the terms that have the logarithm of the determinant. Okay, so that's a formula. And now the funny thing is, of course, okay, the difference of logarithms, I can also rewrite as the logarithm of the ratio of the two arguments. So will become logarithm of det c divided by det c nu. And then the determinant has also many interesting properties. So the determinant of the inverse of a matrix is 1 divided by the determinant. And if I have the product of two determinants, I can also say it's the determinant of the product of two matrices. So taking this all together, I can actually simplify things, and I can say, aha, This is the logarithm of the determinant of C times the inverse of the new one. Yeah. But we know the inverse of the new one. We just had this. This is C to the -1 and then this one. And now things simplify because C is multiplied by C to the -1. And so I just get, well, I could leave away the magnitude sign. The correlation matrix is positive. And so I would just have determinant of 1 plus 1 over sigma squared C times this funny matrix. So that's what I need. Okay. So now you are stuck with this problem of calculating the determinant of a matrix, which is almost the identity matrix. That would be easy, plus another matrix. And that's a little bit harder. But I claim if you look at it long enough and think about how a determinant is taken, you actually find this is the same thing as the log of 1. And now this is really the number 1. Plus the matrix element of C divided by sigma squared. Okay, C was a matrix, but I can take the overlap with this vector x, which is actually the same thing as Cxx, because remember x just indicated, so to speak, the position where I have the only non-zero element. So Cxx would be just picking from the correlation matrix this one non-zero element. And so if we think about it, what is Cxx? Well, that is the uncertainty at the position x, because that's phi x minus the average phi x squared. Yeah. So that is the uncertainty at the measurement location. And so after all this interesting calculation, going properly through the information gain and using Bayes and so on, what we are being told by this formula is, if you want to optimize the information gain, you should pick the x where the uncertainty is largest. So that's an example where this heuristic of going for the largest uncertainty is actually precisely correct. This is the best you can do. Okay, so that's nice. So the typical intuitive way to think about these things is the following. I could now plot versus x this uncertainty, so the fluctuation strength of my Gaussian random process, and I don't know, maybe it looks like this. And then I will pick the location of the largest uncertainty, which is obviously here. And once I measure there, of course, immediately the uncertainty at this spot will be drastically reduced. And most of the uncertainty will then be at other spots. So after the update, I will have something like this. Maybe, I don't know, something like this. And now I can again look for the biggest uncertainty. And okay, now it's a little bit difficult. Maybe it's on the left-hand side, I don't know. And make a measurement there. Again, that drastically reduces the uncertainty at the spot. And the rest will be relatively unchanged, possibly, and so on and so on. So you see every new measurement picks the spot of largest uncertainty and drastically reduces the uncertainty. And there's one special point here. We already said that the correlation matrix will be updated in a way that does not even depend on the measurement result. So it only depends on where you took your measurement, but it does not depend on the actual result you got. Phi bar is different. Phi bar, the average of the Gaussian random process, does depend on the result, but correlation matrix does not. And so as a consequence, figuring out these spots of largest uncertainty is completely independent of the sequence of measurement results you got. And in this sense, it is still choosing the best measurement location, but it is not really adaptive. You don't need to know what were your measurement results. In fact, you can plan this whole sequence of different X location in advance. You don't need to carry out a measurement and then you rethink and then you say, oh, I should measure there or there next. No, this is not necessary because the updates of the correlation matrix do not depend on the measurement result. So that's quite important to know. And this is a specialty of Gaussian random processes. So the previous result does not affect C. And so our active learning strategy for Gaussian random processes is actually independent of these results and therefore can be planned in advance. If you know for the prior distribution this plot of the uncertainty, then you can just plan the first X, and after that, with the right update, which you can do without knowing the measurement result, you plan the next X and so on. Just a moment until I answer the question. It's maybe also a little bit boring because that means these Gaussian random processes, which we have fully under control, which are easy to handle, do not yet display the full complexity of active learning. Oh, isn't it a bit of an unpractical assumption to think we know the uncertainty of the random process at each point? Oh, with uncertainty, of course, we never mean the deviation from the true values. That can be anything. This is all just relying on some prior. And of course, that's our subjective assumption. So people might say the total fluctuation of the values is constrained by some Gaussian. And yes, often it will be just an ansatz. Of course, if you try to do these experiments many times, you can even start to fit your Gauss. So if you have many examples, you could start to fit to these examples a Gaussian random process. And then if you encounter the next unknown situation, you have a pretty good prior that is not just guesswork, but is obtained from looking at many independent examples. Yeah. But that's the thinking. And we will not completely get away from this thinking. So we always need, in this kind of base ansatz, a prior distribution. Maybe you got it empirically by looking at many independent examples. So that's already something. Or you just exploit your general knowledge of the situation, and it's a little bit of a guess. Yeah. But we also said that sometimes details do not matter very much for this Bayes approach. So, for example, someone would have a different prior uncertainty, and it looks like this. Yes, sure. You would have a different location where you measure first. But eventually you will also try to cover all the possible X values relatively uniformly to decrease the uncertainty more or less everywhere by the same amount. And so maybe some of the aspects of your assumed prior distribution will vanish eventually. But it's the old criticism of Bayes approaches that someone has to give you the prior, and this is a little bit a challenge. Okay, so this is Gaussian random processes. Let's now move one step further, so it gets even more interesting. And let's move away from Gaussian assumptions. Let's say I have an arbitrary neural network model, and let's see what we can do there. But we will do it in a way that we very quickly come back to some of the mathematics that we have been able to use here. Okay. And so that's applying the same techniques, but now for neural networks. And I rely on a very nice work by McKay. And I will put a link on the website. So now our model is really an arbitrary neural network. So f theta of x, that's, so to speak, our model, gives some y, but the y is this f theta of x plus some noise. Now the noise, again, I want to assume being Gaussian and have some spread sigma, just like before, same thing. Little change in notation. Now, since for neural networks, we always call the parameters theta, I want to do the same here. But of course, the meaning of theta here is still the same as in everything we discussed before. So this is our lambda. These are our model parameters. Okay. And now I want to apply Bayes. So that comes back to something that we briefly remarked on when we first discussed neural network learning, namely what's the relation to Bayes? What's the relation of the loss function to Bayes? And here we will take it one step further because we will take serious the noise around the best solution. So let's imagine I have obtained several measurements, or for a neural network, we would say I have several training examples where I know the correct result. So I would say P of y of x1 being equal to y1 and y of x2 equal to y2 and so on, given some theta. Well, that's just a Gaussian distribution because I assume my noise is Gaussian, and I will also assume that the noise is independent Gaussian at each possible location x. So what I get then is the following. Again, a Gaussian distribution, and I just sum up the contributions from all these measurement results. There are m of them, and in each case I take the square of the difference between the assumed yj, the measurement result, and the f theta at this spot. So that just means, yes, the noise, the deviation is Gaussian. And there's a little prefactor, so 2 pi sigma squared, I suppose, to the m. Okay. Good, so that is, so to speak, the model, what we call the model. So measurement results given the parameter theta. Yeah. What is the prior? We also need a prior, of course, we will never get rid of this. Well, in order for this to make sense, we need some kind of prior. And I will now simply call it e to the minus L0 of theta, with some normalizing prefactor if I need this. And so the way to think of this now is this prior I can understand as being a regularization imposed on theta. So all else being equal, which theta values are preferred? Well, that's given by this prior. And so I called this L0 because that's like a loss function. And in particular, that's my regularization loss. And we have learned several possibilities there. And one of them was, for example, L1 or L2 loss. So we would have the L1 or L2 norm of these theta parameters. So that's how the regularization comes in and how we would define the prior. And if I'm into defining loss functions, I can also do the same here. I can, up there for the model, I can say, aha, this is also a loss. What kind of loss? Well, it's some mean squared error loss between the data points yj and the model predictions. So this mean squared error loss depends on theta and on this particular set of measurements or training samples that already exists. Okay. So now I can write down Bayes. I can just multiply the two, the prior and the model. So Bayes now tells me, if I simply apply Bayes, what is P of theta given the measurements or given the training samples? Well, it's proportional to e to the, and now it's convenient, I can just add the terms in the exponent, e to the minus L0, that was the regularization loss, plus the mean squared error loss for these training samples. And all of that could be understood as somehow the loss, the overall, the total loss, given the current training samples, given the current measurements. And so now you see, this is going a little bit beyond what we had said before when we first discussed the relation between Bayesian and neural network training. There we just said, oh, now you would minimize the loss. But in the present case, we will take this serious. We will say, no, there is a probability distribution, so theta can fluctuate. So we would have a situation like this. Here's theta. That is my loss function. Maybe it looks like this. That's the overall loss function. And then I would have a probability distribution after the measurements have been obtained. So it might look a little bit like this. So that would be the P of theta given the measurements, the posterior over theta. And now what we typically do in neural network training is we're looking for the lowest loss. So we would do gradient descent until we find the best theta, which in this case would be here. So let theta star be the minimizer of L. Okay, so this is what we usually look at, but now we will take the fluctuations serious. And in order to take the fluctuations serious, but not to have too much trouble, I want to imagine that the probability density really looks like the one shown here. So everything is quite concentrated around a deep minimum. And around this deep minimum, the loss function can be expanded in quadratic order. And that would also mean then that the probability itself looks like a Gaussian to a very good approximation. And so in order to do this expansion, I will now also imagine that I can look at delta theta as the deviation from my optimal theta. And so I can now say in a Taylor expansion, L is the L at theta star plus a linear term, but that vanishes because I'm expanding around the minimum. And then a quadratic term. And the quadratic term, as usual, is, well, the second derivative of L. Now, L is, of course, L itself is a scalar, but it is a function of many parameters. So if I write this, what I really mean is the second derivative matrix. So it's the Hessian. And that is then multiplied by the deviation vector. So delta theta is a vector and the Hessian is a matrix. And in components, this would be, of course, as we always say, taking the derivative with respect to theta L and theta J. And now my Hessian, because in a moment I will be inserting it into the exponent of my probability distribution, really is a correlation matrix. It becomes a correlation matrix. And there you see immediately the connection to what we had said a moment ago. So, well, I don't even need to write it down. Up here, we say the probability is e to the minus L. I have expanded L to quadratic order around the minimum. And the quadratic order simply can be interpreted as what you would get for a multidimensional Gaussian distribution with this correlation matrix, which is the inverse of the Hessian. So C is the inverse of the Hessian matrix. And so then finally, I would say, in particular, for example, the fluctuations of delta theta can be immediately read off because they are given by the correlation matrix. So delta theta L times delta theta J averaged over these fluctuations, over this probability distribution, equals CLJ. Of course, that's approximate in the spirit of our expansion to quadratic order and approximating it as a Gaussian, but then it's true. Okay. And so now we want to imagine that we are doing a new measurement at some still freely chosen location X. And of course, again, we want to optimize over X. We want to see at which point do we have the biggest reduction in the entropy. So that's the goal now. So let's do a new measurement or provide a new training sample. And what that just means is in our mean squared error function, we just add a new term. So we would say my loss is the old loss plus a new term, which just describes the measurement at the new location. So let me just call this y and then f theta of x. So that's the new term. And so now we have a modified L. The theta, the optimal theta value will shift slightly. So that's one thing that happens. But also the curvature with respect to theta will, of course, change. And so I could say my Hessian changes. So I will say I will have C to the -1, the new inverse correlation matrix is the old one, plus the second derivative of these terms. And that would be, I write first down something and then I have to say a little bit about an approximation that we are doing. But that would be in particular what you get if you act with your theta, with your one of your theta derivatives on this f. So the f theta comes in squared. And you can act with one derivative on one f theta and the other derivative on another f theta. And then that would be df theta of x over d theta L. And the same again for theta j. So that's one part of the story, at least. Now, it's not the only part of the story, and this is where things become a little bit tricky. So there would be other terms like if you apply the derivative twice on one of the terms in this squared expression. And so then you would have something like this here. And to keep things simple, I will at the moment assume that y is even just a scalar. So it's difficult enough this way. Otherwise, I have even more indices. Now, the second part may be small. You realize that if we did have a completely linear model, so if f theta would be linear, then the second part would completely vanish. Now, if f theta is not entirely linear, it doesn't completely vanish, but there can still be situations where this second part may be small compared to the first part. If that's not the case, our analysis has to be expanded and has to become more complicated. And I will assume that here now. Now, if that is true, we only need to consider the terms up here. So these terms. And I will give a little name to this. So this, if f is really scalar, this is now a vector quantity. And I will call this vector g. The particular quantity shown here would be the component j of g. G stands for gradient, obviously. So what I can do now under this approximation, for sure, is again, I can work out the entropy reduction. And again, it's not very difficult because under the approximation we are doing, everything is a Gaussian. We know the entropy of a Gaussian. We have the log of the determinant of the correlation matrix. And we can follow the same calculation as above. So I don't need to repeat everything. But what I get then eventually is something like, okay, under our approximations, something like this. Okay. So now it looks a little bit different than before, but still you recognize the similarities. So what you see is here the correlation matrix enters, that's fine. We know this is the inverse Hessian of the loss function at the best spot, theta star, so that's nice. We also know that here the measurement uncertainty enters. Of course, you have a larger entropy reduction if sigma is smaller, because then you have a more precise measurement. That makes sense. And you also have this gradient vector, which is, so to speak, the sensitivity of the outcomes of your model with respect to the parameters of the model. And so what this part here represents is again the fluctuation, just like before for the Gaussian random processes. So we can prove this for a moment. So we can look at what is the fluctuation of my model predictions, f theta, at this particular location x, due to the fluctuations that theta has. So remember, we no longer assume that we have a neural network where theta is already optimized and at its perfect spot, but theta can fluctuate because the loss allows it to fluctuate, and we are adopting this Bayes framework. And then you could say, the variance of f theta because of these theta fluctuations is, if you expand things, would look like this. And now you see, so there's the delta theta term, but that's our correlation matrix. And then there's this df over d theta times df over d theta terms. Well, but these are our g vectors, so to speak. So you can write this as 1/2 G transpose CG, and that's exactly what is written up there. Yeah. So now you see again an example where the information gain, now with some approximations admittedly, is largest wherever the uncertainty is largest. So we could again plot the expected information gain against x. So that's the expected information gain, 1/2 log 1 plus 1 over sigma squared, and then I can rewrite it as the variance of these predictions. And I can get something like this. And if it looks like that, I would, of course, pick the x that maximizes my expected information gain. So two things enter here. What enters is the Hessian of the loss function. So c to the -1 is the second derivative matrix. That tells me how large are the fluctuations of theta, how uncertain is my model still. And what enters is this g df over d theta. So what's the sensitivity? How much does the output of my model change when my theta fluctuates? Both of these things enter, and that makes sense. And then when you make a measurement at this particular location x, you will do the best in order to reduce these fluctuations. And so there's one nice thing about this case as opposed to Gaussian random processes now. The updates do depend, the updates in C, for example, the correlation matrix, during the learning, they do depend on the previous measurement results because we have this non-Gaussian distribution, because not everything is linear and not everything is quadratic in the exponent. So that's nice. So because C depends on the previous measurements, that means also the best choice of X, so the X star that I will choose depends on those. And that means we really have an adaptive strategy. We have to look at what is the result of my measurement. And depending on the result, I will get one or the other choice for the next measurement to do. Yeah. So that's nice. What's not so nice here is that, of course, now the parameter space is really large. It's no longer like with these physical models where you maybe have a handful of different parameters, but theta is all the weights and biases of a neural network. So there may be thousands or a million of these parameters. And at least the way it was formulated here, of course, you would need the Hessian, which is the second derivative matrix. Now, it can be done in principle with automatic differentiation, but it may be expensive. And so one of the remarks I still want to make here is a very nice remark, namely, since we are now taking serious the fluctuations of theta, and that's encoded eventually in the Hessian because that's the inverse of the correlation matrix. Since we are now interested in these fluctuations, there is actually a way to sample from these fluctuations, and doing so in a way where you basically run the standard stochastic gradient descent with a slight modification. And this is something that I still wanted to discuss briefly. It was very nice, actually. So imagine you have this loss function, and for a physicist, this looks like a potential. Yeah? And now imagine you have a particle that has the tendency to slide down this potential. That would be like gradient descent. Yeah? So the velocity, the change is like the gradient. So it goes down the hill. But then you add some noise, so it will wiggle around. Yeah? Now, in order to describe such a situation, you would say, well, a physicist, I suppose, would say in a continuous time formulation, theta would become a function of time, and you would have something like minus eta dl over d theta. So that's the minus the gradient, you're sliding down the hill, plus some psi of t, that would be some Langevin noise force in continuous time, which would look like white noise. But we know that when we apply these things to neural networks, we do not really solve continuous time. We have discrete time. So let me write it in discrete time. We would say theta at t plus 1 after one update step is actually the old theta minus eta, my learning rate, times dl over d theta, plus, and now I will do the same. I will say there will be noise. And it's not just the sampling noise from my batches. That's another kind of noise, which we try to ignore here for the moment. But it is actually the kind of noise that I was talking about here. And now there is a very nice insight from statistical physics. So this kind of behavior is analyzed all of the time in statistical physics. And people know the following. If I now have my noise being independent at different times, so that's white noise, and the variance at a given time is 2 times eta, then the result will be that if you run this process long enough and you look at theta, where it ends up, and you tabulate it, so to speak, if you figure out the theta distribution, it turns out to be simply a Boltzmann distribution, and it's the Boltzmann distribution for this loss function, for this loss function that plays the role of a potential. So this, and it's even independent of eta. It's independent of eta if we choose the noise in just the right way, like shown here. Okay. And so this is a result from statistical physics. If you have this kind of Langevin equation with sliding down the hill plus white noise, and you make the strength of the white noise correct, you get a Boltzmann distribution. And that's exactly the distribution we are after, right? So that's the distribution that you get if you did your Bayes update, starting from the prior and starting with all the measurement results, combining them towards the full loss function. That's the distribution we want. And so now this Langevin approach is exactly a method in principle, at least, to sample from this distribution. So what you will have is that you could plot, say, theta. I now treat theta, say, only one of the components, theta 1, let's say, as a function of time, and you will see it fluctuating around And then you can take statistics from these fluctuations and you plot the P of theta distribution, and you find it's exactly given by e to the minus L. And that's exactly what you wanted. So in principle, these theta fluctuations can also be sampled. So this has been realized, of course, also in the context of machine learning. I'm not aware that people use this really very much in practice. There may be multiple reasons, I guess, but conceptually, at least, it's a very nice way to use something that we know from statistical physics and apply this to neural networks, which then is conceptually, I think, in principle, much better than saying, I initialize theta somehow randomly and I do gradient descent to find the minimum of the loss function. Maybe I get stuck, maybe I don't get stuck. And then I take whatever I get after a certain number of training steps. So here in principle, you say, there is my model parameterized by theta. There are my observations. Let me apply Bayes and let me sample from the resulting theta distribution. Okay. Yeah, so this is the story for today. Are there any questions? Maybe I should point out that the eta up here and the eta down there, they have even different dimensions, obviously, because the theta up there, that was a differential equation. So eta would be looking like a rate if everything else is dimensionless. Whereas down here, it's really only a number. Okay, any questions? Active learning, optimal experimental design, Bayes. If that's not the case, I can already give a preview of what we will be doing next week. So next week is the last week of the lecture series. And we will come back to complexity that has to do with our initial discussions of Shannon entropy. And we will ask, if you want to have the least complex model of the world, how do you go about this? And so that's a very interesting question. Okay, so then I would say, see you next Monday.